Module 11, Part 2. Right there. Alrighty. If you would, turn in your textbooks to page 364. Let's just remind ourselves of where we were last week. So we introduced solutes and solvents and solutions. All right. So and then we talked about various things, but we introduced. We haven't introduced molality yet, but we did introduce last time in the last module the concept of molarity. And so today I get to offer you something else that will be delightfully confusing because it's so similar sounding to molarity, and we'll see that in just a minute. Before we left, we talked about the exothermic process and the endothermic process, and we gave the best illustrations of that in terms of, well, they're not the best. Burning wood is an excellent illustration of an exothermic reaction, as you well know. Add energy to a piece of wood and you feel the heat that comes off. But an exothermic process is something that releases heat, and an endothermic process is something that retains it. And we use the illustration based on the pictures on the bottom of 364, those warmers and those icy packs that some of you have used, either trying to stay warm somewhere or trying to ice an injury maybe. But either way, those are examples, classic examples of what we mean by a chemical reaction that either absorbs heat or releases it. And so with that, we have reached the page 3 of your notes, and I know you're thrilled, but let's just go through an example of applying stoichiometry to solutions. And it's really not much. It's just involved using the molarity formula. Other than that, it's what you've done several times, but let's remind ourselves one more time. So what I've done is taken example 11.1 from page 365 and put it in your notes. So if a chemist mixes 50 milliliters of a 1.23 molar solution of, I don't know, sodium carbonate, I think. Yeah, it must be sodium carbonate. With excess calcium hydroxide, how many grams of calcium carbonate will be produced? And so in the example, they gave us the balanced chemical equation, and I've given it to you too. So there it sits. We know how many milliliters we have of a certain molarity solution of that sodium carbonate. And we know that the molarity equation is the number of moles over the number of liters. And as a result, then the first thing we got to do is fix milliliters, because they just love to do that to us. They love to mess around with units and remind us of Module 1. So here we go. Let's fix milliliters, and we didn't go through the factor label method in this instance, but that's the bottom line. 50 milliliters is 0.05 liters. So now that we have liters, we have molarity, and so we can figure out moles, all right? Because again, molarity equals moles over liters. So we simply have to rearrange the equation, and in order to do that, you multiply both sides by liters, and the liters cancel on the moles over liters side, and then you end up with liters times molarity, which is going to give you the number of moles, and that's what you see in the next step. So the number of moles equals the molarity times the liters. We've got 1.23 molarity, and we just multiplied that by the number of liters, which we rearranged from milliliters. So now we've got moles. Now we've got something we can plug into a balanced chemical equation, compare moles based on the balanced chemical equation, solve for the moles of the stuff that they want to know, and then convert that to grams. And that's what we do here. So remember what, in terms of comparing moles to moles in the balanced chemical equation, the stoichiometric coefficients are the numbers to the left of the individual chemical formula of each one of the compounds. And when you don't see a number to the left, it means that it's 1. And that's what we've got here, since we were given the sodium carbonate. We're gonna cancel that out, 1 over 1, and so we immediately know that we've got 0.615 moles of calcium carbonate. Well, the last step, since we just discovered moles, is to solve for grams. And how do we do that? We go back in time and we look at our fabulous periodic table, and voila, we add up the total number of grams per mole in each one of those items in the chemical formula of what we're solving for. In this case, 1 calcium, 1 carbon, and 3 oxygens, and that's what you see there next to the end of the equation. Calcium was 40.1, carbon's 12, 3 oxygens is 48. You add all those together and you got 100.1 grams per mole. So now you know how many grams is in 1 mole of this stuff. And so in terms of doing the math, you set it up so the moles cancel and you end up with grams, which is the 100.1 times the 0.615. So we've been there, we've done that, we've seen how this stuff works. All it is a matter of plugging in different formulas. In this instance, excuse me, we always have to pronounce it the way Mr. Krabs does, formulars, all right? So it's just a matter of plugging in the different formulas and solving for what it is that you need, and then taking the steps. There's not a thing that's hard about this other than keeping track of the steps. And we've said that all along, and I think most of you have got that. Some of you still struggle, and if you do, if you find yourself struggling with that, well, the only thing I can tell you is talk to me or look it up yourself. Is there questions about that? So as you're noticing, we're finding stoichiometry in just about everything at this point in time. And that's, again, just the way the course works. We can do stoichiometry for just about everything. And again, it makes sense in terms of this basic chemistry, determining how many moles or how many grams that we're using in a given chemical equation. Is there questions about that? Now, I promised you, and I always like to keep my promise, of something that's going to be delightfully confusing today, and so here it is. So we just reminded ourselves about molarity. We learned that in the last module. Well, now we get to learn something called molality. So yeah, we've got molarity, molality, molality, molarity. Say that 10 times together. So there you go. And it's just there to confuse you. That's all. That's all. That's the only reason in the world that we would offer this, is just because we like to confuse. So that way it makes us look smarter. I'm kidding about all that. But the reality is they're very similar, but what they tell you is actually quite different. So molality is another unit of concentration. That is, after all, what we're talking about. And so if you would, if you turn to page 367 and write this down, molality is, just write it in words, you're going to see it in formula just below where you write it, but molality is the number of moles of solute per kilogram of solvent. That's all it is. So it's the number of moles of solute divided by the kilograms of solvent. That's molality. All right? All right. Looks a whole lot like what we're talking about with regards to solutions, right? But this has to do with the concentration of a solution. So here's the defining difference between the two words, other than, incidentally, molality. It's abbreviated with a small m. Not to confuse you, of course, with the small m abbreviation for mass. Not that we would want to confuse you, of course not. But it happens to be the small m abbreviation, and molarity is the capital M. So that's the way you tell the difference. Now, the difference between the two I've written for you right below the definition in terms of number of moles over kilograms of solvent. And incidentally, once again, this particular equation is units sensitive. It has to be kilograms. So when they sneak in milligrams or grams or whatever else, you're going to say, aha, I know what you're doing to me again. You're trying to confuse me. It's all about confusion. It's all about trying to make me look bad. So, but you're going to say, no, I understand this now. I know what you're doing to me because I know molality has to have kilograms, not grams. So, molarity divides the number of moles of solute by the total volume of the solution. And so what you're looking at with molarity is volume. All right? Well, molality, and I capitalized it, it's terrible, but molality divides the number of moles of solute by the number of kilograms of solvent. And what you're solving for there is mass. So that's the distinguishing feature of both of these concepts which produce equations. And we love them equations, don't we? Yes, sir. I'm going to chemistry this Thursday to get me some equations. Well, I've satisfied. I've come through for you. I've delivered your equations for you that you've been looking forward to all week long. So there we go. Now let's look at a molality question on page 368. We're actually going to move right along today. This is a good thing. It's not a long module, and there's basic concepts. We'll put it this way: the concepts are there's not a lot of them. Let's describe it that way. So a chemist mixes 3.4 moles of sodium chloride with 4.5 kilograms of water. Oh, look what they did. They provided the right units. So all we have to do is look at the equation for molality and plug those things in. What is the molality of the resulting solution? So we know that it's moles of solute over kilograms of solvent, and they gave us moles and they gave us kilograms. So all you do is put the numbers down and do the math, and you've got it there. And in terms of it, the answer, notice how they do that: moles of sodium chloride per kilogram of water, or molality. All right, so you divided the 3.4 moles by the 4.5 kilograms, and you got the 0.76, and that's molality. All right, simple. I mean, it really is. The hardest part of these things, that, as you have noticed for the longest time since we've been using these formulas, is just trying to figure out what you got and what the formula requires, and if you have to change any units. That's the hardest part, is just reading the question and understanding what they gave you and what you're trying to do. Look at the one next to it, below it. So in this instance, what they've done is messed you over in two ways. Number one, they gave you grams, and number two, of zinc chloride, and then they also gave you grams of water. And so you're just disgusted when you read something like that. How could they do that to me? Why would they give me something like that? And so what you have to do then is change grams of the zinc chloride into moles, right? And the way that you're going to do that is the way we just did it with the stoichiometry. You're going to go to your handy dandy periodic table, and you're going to look at each one of the items in the chemical formula and add those together and do your factor label method to cancel for grams in order to solve for moles. So in this instance, 1 mole of zinc chloride adds up to 136.4 grams. And so you set it up that grams cancel, and you end up doing the math, and you've got 0.330 moles of zinc chloride. Well, you fix that one. Now you got to do the same thing and fix grams of the solvent. So once again, you're going to do the factor label method to get rid of grams and solve for kilograms, and you know that 1 gram is 1,000 kilograms. Do the math. Now you're in business. All you got to do is plug that in to the formula, and there you go. And so the answer is 2.20. So let me stop there for just a second. We're going to add 2 more formulas for you this morning. We'll explain them. And these are a little more complicated. They're not hard. It's just going to require you to think a little bit. And once again, to recall what you've learned earlier in terms of the way that compounds bond. Are they ionic bonds, and how many ionic bonds are involved? Remember, you drew that in terms of the various compounds, what they would look like. We did shapes in the last module, and as a result, you have an idea of what these things look like. So, and we're going to discuss that in just a second. But is there any questions about this fabulous new formula, molality, and how it relates to molarity? All right. Okay, good. Again, you know the drill. If you've got, you get home and you look at this stuff, and everything starts to go dark in your mind. You know the email address, where to find it, you know where the phone number is. Just call. It's really easy stuff, ultimately, although it just requires tracking. That's it. And that's what we're going to see now in these next 2 concepts. So what we're introducing now is freezing point depression. That's defined for you on the bottom of page 3. And boiling point elevation. These formulas are identical with respect to one thing. Freezing point depression has a negative feature to it. At the front end, it's minus I, as we will see. And boiling point elevation has no minus, it's a positive. All right, and we'll explain it to you, Lucy, why that is right now. So we are actually on the discussion of this thing begins on page 369, and it's a good discussion, and it's this really the discussion I'm going to have with you right now. So let me define it for you. I'm on the bottom of page 3. The freezing point depression, when a solute is dissolved into a solvent, the solution always has a lower freezing point than the pure solvent. All right? So who of you here, in our town, unless it's really bad, unless there's lots of ice, they're never really going to do much. Although I take that back, they did something. I think they had sand out on the overpasses on Research Park Boulevard, but I don't know if they actually put down salt. I think most of the time they use sand. Yes, sir.
They put salt down in Huntsville.
They put salt where?
They put it out in South Huntsville and then parts of Grove as well.
Did they really on the roads? And you probably noticed that if you go shopping anywhere. I know Target always has salt out in front on days like this. So why do they do that? Why do they want to make the roads salty? Right? And of course, if you ever lived up north, you know all about that. And you are saying bad words under your breath if they haven't been out to plow and salt, because the roads are just a disaster to try to drive on. But why do they do that? Well, just because. Yes, sir.
Melts the snow.
It does. It does. And what we're talking about with regards to freezing point depression is why. All right. So yeah, when you put salt on icy, snowy roads, it melts the salt or the ice, at least for the most part. Now, you know, if it's really, really cold, sadly, it's not going to do a very good job. But in terms of doing a pretty good job for pretty cold weather, and certainly the weather we get around here, ice is the ticket. All right, excuse me, salt is the ticket, and or sand. Sometimes they put sand down, and even though sand doesn't dissolve, there's a friction aspect of sand that elevates the temperature such that the ice or snow will melt. Well, what we just read it one more time. Yeah, here we go. When a solute is dissolved into a solvent, the solution always has a lower freeing. Yes, sir. It frees that point. Would you please freeze instead of free? Freezing point than the pure solvent. That's the reason. So when the salt hits the snow, even though both are, you know, in one respect solids, right? Still, there is a dissolving going on there. The solvent is the ice and snow, and the solute is the salt, and they begin the process of allowing those molecules to come apart. All right, remember the sodium chloride in terms of the ionic compound that is. So they break apart in terms of those little electric attracted bonds, and they're not bonds, but that electric attraction, and the chase begins, all right, between the sodium and the chlorides and the water. And I've described for you on page 4, if you turn over in your notes, this process. The reason for freezing point depression is when a solute is dissolved into a solvent, the solute molecules, or ions, remember that's what they become, begin moving around in the solution. And the solvent molecules are attracted to the solute, and a chase begins. All right? And the mutual attraction between the solvent and the solute molecules adds more energy or heat to the chase. In order for the solvent molecules to slow down and stop moving, in other words, to reform a solid, more energy must be removed, and that's called a drop in the temperature in terms of the weather. The only way for this to happen is, I just said it, is by lowering the temperature. Thus, more energy must be removed from a solution in order for it to freeze than a pure solvent. All right, so we've just found out why, and we always knew it worked. Now we know why it works in terms of get that salt out there, all right, over those bridges, especially around here, that tend to freeze. So that's what's going on in terms of freezing point depression. And it's not that the freezing point is so, I'm just so down. Oh, I think I'm just going to lay in the bed all day long. No, it's not going on that way for the freezing point. It just means that the freezing point is decreasing. It has to be colder in order for a salt and water solution to freeze. All right? Questions about the concept? Pretty simple, isn't it? Yes, sir.
So how much colder does the salt make it before it has to freeze?
Well, it actually depends on the amount of salt and the amount of water. And you've just led us in to solving that question. You wanted that equation. I know you did. We all wanted the equation, and you got it. Yes, sir. There it is. When a solute, this is page 4 of your notes. When a solute is dissolved into a solvent, the resulting change in the freezing point temperature is determined by the equation. Yes, sir. Yes, sir. And there it is. Triangle T equals minus I KF M. And so you get to guess which one of those M's is. Is that mass or is that molality? Well, only the equation knows. We'll find out in a second. So, I is negative, and that's the difference, as you will see, between that and boiling point. And incidentally, just as an aside and a fast explanation, we'll go over it again in just 2 seconds, but well, it'll be longer than 2 seconds. 1, 2. We didn't go over it. So, it works the exact same way for boiling point. If you dissolve something into a solution, it's going to boil at a higher temperature. You got to get it hotter in order for it to boil. In a solution, when you have something dissolved in it, it's got to get lower to freeze. It's got to get higher to boil. Okay, the temperature that is. All right, so I is negative because of the decrease in temperature. That's what we're talking about here. Delta T, or triangle T, is the change in temperature. We've seen delta T before. Oh yeah, we've seen delta T. But we've never seen I. Oh boy, now we got something new to confuse you with today. And it is a little bit, I mean, I'll give it to you. This is not the easiest aspect of equations because you're going to have to think about it a little bit. But I is the number of molecules or ions that the solute splits into when it dissolves. So, we dissolve salt into water. So, how many ions does sodium chloride produce? Thank you.
2.
Thank you, exactly. A sodium ion and a chlorine ion, all right? And that's simple, but the problem with it is the solutes get a little more complicated. And so it takes a little bit of thinking to come up with what that might be. The first example on page 371 uses sodium chloride. So that's pretty obvious, right? And I probably on the test won't try to confuse you. But look at, turn over to page 372, and we're not necessarily going to do the problem, but look at what we're talking about here. We're talking about aluminum nitrate. I think that's what that is. And look at the formula there for aluminum nitrate. It's Al, and remember what we got there in terms of the polyatomic. We've got NO3, and you always deal with that as if it's a single element, right? So it always goes in parentheses, and in this instance, there's 3 of them. All right. So the question is, how many ions does that stuff break into? Well, anybody want to take a shot at that? Of course, the answer is right at the bottom. Yes, sir.
I would guess 10.
Say what?
I would guess 10.
No, that was a good guess because what you did was count all the elements. But in this instance, since the NO3 stays together, what you're talking about is 4. All right? So, great question, great guess though. And that's what makes it tricky, all right? Because sometimes you'll have these polyatomics which always stay together, and you'll be tempted to want to break those down even further, but no. They are married for life. Nobody can break them up. All right? So in that instance, there's 4. So I is the number of molecules or ions, and notice molecules in this instance, the NO3, that the solute splits into when it dissolves. So you count them up. and that's I. All right? Now look at KF. KF is the freezing point depression constant. As it turns out, every solvent has its own unique KF. And so you ask, why the F? Well, just to further confuse you. That's all. Now, it's ultimately to keep the units together. All right? If we don't have a unit on this particular thing, it's just easier to solve, to eliminate, to cancel units and to solve the equation. So when you do these things in terms of any of the questions in your textbook and on the test, you will always be given the KF. You know, all right? There's nothing to memorize. There's no table that you need to find and memorize. You'll always be given the KF. So that's a constant. And then the last one, okay, is it mass? Is it molality? What could it be? The small m is there. What's it there for? Well, it's there for molality. All right? So you tell me what they're going to do to you in this instant. In these equations, in these questions, what they're going to do is not give you molality. They'll give you two aspects of molality and ask you to solve for the molality and in order to get there. All right? So that's how they'll try to confuse you, but it's still not confusing. The hardest part of this equation is, well, number one, in terms of freezing point depression, remember in the minus, because you're going down in temperature. And number two, I'd probably reverse them. Number one is I, trying to figure out the number of molecules or ions that the stuff breaks down into. And then the next thing is the minus, just to make sure you plug in the minus, because every year I get a positive number in terms of these freezing point depression questions on the test. And you know, you just got to take off something for that. When you do the math right and set it all up right, I mean, it's depression, it's decreasing, not increasing, all right? Because that, as we're going to see in 2 seconds, is boiling point elevation. All right, so in terms of this, I guess we can do a quick example. And let's do the easiest one, because I'm not going to try to confuse you on the test. All right, when 15 grams of sodium chloride are added to 100 grams of water, what is the change in the water's freezing point? And that was a question asked just a moment ago in terms of, well, what is the overall change? What is the temperature at which it'll start to freeze when I add salt to whatever it is that I'm adding it to? And, you know, when it comes to roadways, there's not a guy out there saying, let's see, I got 12 pounds of salt, I got 10 miles of road, no, I need another. That's not happening. He's dumping the salt in the hopper and pouring that stuff on the road as he goes, all right? That's what's going to happen. But you, as a chemist, well, you want to know exactly what temperature it is that if you add a certain amount of salt to that water, that it's going to take to freeze that particular amount of salt water. And so what they did is gave you 15 grams of salt. That's added to 100 grams of water, and they want to know what the change in the water's freezing point. And then, lo and behold, looky there. They gave you the KF of water. They always will. I always will. It's my solemn promise to you. I will always give you the KF. So, what we got to do in order to do this, of course, is to find molality, because we don't have molality in any aspect of that. What we got, sad to say, is grams of water and grams of sodium chloride. So, and in order to find molality, what do we got to do? We got to have number of moles over number of kilograms of solvent. So we don't have any one of those. It's because they want to confuse you. And so you're going to defeat them, though. You're staring them in the face and saying, you will not confuse me, because I know what you're trying to do by giving me different units. I'm going to solve for those units. And that's what we did right there. We solved for the number of moles of sodium chloride. And how'd we do that? The way we've always done it. We went and looked up the grams per mole of sodium and chlorine on your periodic table, and we solved so that we could get rid of grams and keep moles, which meant you divide the 15 by the 58.5, so you get 0.256 moles of sodium chloride. So you got the top half of the molality equation done. But look what they did. They gave you 100 grams of water, and you know that it's kilograms of water, and you're not going to let them get away with that. So you're going to change grams into kilograms, and that's what we did there with our equation. We changed grams to kilograms. Now we can solve for molality, and that's what they did. They put the moles over the kilograms, so you have 2.56 molar solution, okay? Well, excuse me, molal solution. So you've got two aspects of your formula, all right? You've got the constant because they gave it to you. You just solved for molality. The last thing you got to do is figure out how many ions sodium chloride breaks down into, and we already said what that was, and it's just simple. It can't be any more than 2. It can't be less than 2. It's 2. So you have the equation then ultimately of we'll turn over and just look at it so you can see it. So the change in temperature is equivalent to the minus I, which we said sodium chloride breaks down into 2, so there's minus 2, times the constant, 1.86, times the molality, 2.56. You plug that all into your calculator, and lo and behold, you have a freezing point depression. So what happens when you add 15 grams of sodium chloride to 100 grams of water is that you decrease its freezing point by 9.52 degrees. Kind of cool, isn't it? I mean, in spite of my sarcasm and silliness, that's kind of cool deal. You know, you can figure out exactly how much more of a decrease in this instance of temperature, how much of a decrease in temperature, double my redundancy, what that's going to be. So, pretty cool, huh? Well, guess what? It's the exact opposite for boiling point. Remember, any solute, in terms of it being dissolved by a solvent into a solution, is going to decrease its freezing point and elevate its boiling point. And so that's what we have here. Boiling point elevation, the last discussion on the bottom of page 4. When a solute is dissolved into a solvent, the solution always has a higher boiling point than the pure solvent. All right? Again, we've said it several times, different ways. So the freezing point of salt water is lower than that of water. The boiling point of water is higher than that of water when you dissolve something into that water. All right? The reason for boiling point elevation is actually not the same as freezing point depression. So for boiling point elevation, when trying to boil a solution, what you're trying to do is pull molecules far away from each other so that the substance will change from liquid to gas. That's what's going on there, right? In terms of adding energy to your solution, you're trying to move this stuff, you're trying to get them moving so fast. Oh, I was going so fast. And that's like the one of my all-time favorite jokes. So a snail was robbed, and he was beat up by its assailant. And when the police investigated this, the snail said, I screwed up the joke. It was robbed by a turtle, and the snail says to the police, Well, did you get a description of the turtle? And the snail says, I just don't know. He was moving too fast. So, I tell you. All right, I won't be a comedian. But anyway, that's what's happening to the molecules in the water. They're moving so fast that they break out of the solution, remember, and become a gas. Well, you're trying to do that by adding temperature to a solution, and if a solute is present in that solution, the molecules of the solvent are attracted to the molecules of the solute, making it harder to pull the solvent molecules apart. So the harder they are to pull apart, the more energy, or in the form of heat, must be added to make the solution boil. So that's the difference. Remember, you've got the movement, the chase that's going on, creating heat with regards to freezing. That's why freezing point is depressed. Well, in this instance, you've got attraction. I don't want to go away. I don't want to separate, they say. And so you have to keep adding pressure, well, heat in this instance, not pressure. And as you do, then they will break apart and you will reach a boiling point. All right? And so the equations are absolutely identical, with the exception of boiling point. You do not have a minus. And it only makes sense, right? Because you're talking about how much more heat is necessary in order to reach the boiling point of a solution, and it's going to take more, so the answer has to be positive. It can't be negative, all right? There's an illustration there. Well, I guess what I'd like to do is have you come up and show me your homework. So, do you need to see the illustration, walk through that? Okay, I think you're pretty good. It's the exact same equation with the exception of the minus, all right? So, is there questions about any of it? Hardest thing is how many molecules, so you probably want to practice that. You want to look through the questions that's in the back of the textbook, because it just gives you practice at looking at those things and deciding how many molecules in order to figure out I. You're always given the constant, and then they'll mess with your mind with regards to molality, because they're liable to give you elements of the molality equation instead of just giving you molality. So you have to solve for molality. But other than that, it's all pretty simple. Are we good? Yeah, as good as we can be, huh?